Hi there, my name is Danny and I'm a senior software engineer at Grafana Labs, and I'm here to show you how we scaled up our Memcached cluster 42x in size to solve a reliability problem and ended up cutting costs in the process as well, which was a surprising but welcome result. So in today's presentation, I'm going to be showing you how we reduced our object storage requests 65% using this massive cache. We saw a 2% reduction in TCO through this process, and there was no degradation in performance. You'll see in the bottom right of the screen there's a QR code which will take you to a blog post where we talk about this topic in a lot more detail, and in the slides that follow there will be QR codes as well for the relevant information on those slides. So in order to understand the problem that we had and the solution that we put in place, we need to understand a little bit about how Grafana Loki works internally. So Loki is a log aggregation database which allows you to send logs in any format, and then at query time choose how you want to interpret those logs. And so the way that you use Loki is you have logs in log files. Those are then scraped with an agent like Promptail or Grafana agent. And what that agent will do is it will pull out relevant pieces of information from those log lines. For example, the timestamp at which the log line occurred, and then you can extract some labels that give some semantic meaning to what those logs are. So for example, those could be, as we see over here, like app equals nginx to indicate that these logs come from an nginx application, and env equals dev. And then what Loki will then do is receive create the index and what we call chunks, which are the compressed form of the log data, and store those in object storage. Now, to dive a little bit deeper into how Loki does this, if you have log files from many different applications, like let's say we've got nginx deployed in 2 different availability zones in the cloud somewhere, and so we've got 2 instances of each. So we've got nginx A, B, C, and D. 2 of them are in this US East 1A availability zone, and the other ones are in 1B. We will take all of those log lines, associate the labels to those log lines, and then send those to Loki, and then Loki will compress those log lines down into what we call chunks, give them some identifiers that we can refer to them later, and then store those in object storage. And these chunks are addressable by their stream, and the stream is a unique combination of labels. So when we want to retrieve those logs in the future, what we do is we use a combination of labels to identify the chunks that we need to process in order to get the information out that we need. And so for example, if we wanted to fetch all of the nginx logs for a particular time range, we would just use the app equals nginx label, which would give us all of the chunks in this example. But if we just wanted the nginx logs from availability zone US East 1A, it would give us a subset. And this allows Loki to process queries extremely quickly. So in this example, we're requesting all the nginx logs from a particular availability zone, and then we're going to use a filter here to find log lines that contained this IP address. So for example, if we started from 100 terabytes worth of raw logs, then if we applied this label selector, this would reduce the set of chunks that we have to go and fetch and process. And then we can further reduce that set by specifying a time range. And then once we've got all of the chunks that we need to process, then we process them brute force. And so this approach allows Loki to process massive amounts of data very, very quickly. And it works extremely well for observability use cases. And like relational databases, if you were to do a select star from some huge table, Loki can also be slow if you select all of your logs and do some kind of very broad search like this over the entire set of your logs. And unfortunately, we do see customers using Loki in this way in our Grafana Cloud log service, and this is where we started running into reliability problems. And so the focus of today's conversation is going to be the Grafana Cloud log service, but the techniques that I describe here will be relevant to anybody running their own Loki installation if they're running into some of the problems. So the problem that we started experiencing was rate limiting. When customers run these very broad queries over massive amounts of data, we have to go fetch many millions of chunks potentially from object storage. And these object storage services like Google Cloud Storage or Amazon S3 or Azure Blob Storage, they don't take very kindly to people absolutely hammering their service and requesting a large amount of information in a short space of time, and so they apply rate limiting. And the problem with rate limiting for us is that when we can't fetch information fast enough from object storage, which is our primary data store, then we start seeing a lot of downstream effects. For example, we see decreased throughput. In other words, how fast can we process the queries? And so this results in slower queries ultimately, the users being frustrated. We start seeing our SLO budget burn alerts firing. And this causes toil for our operators as well. And when we're in the situation, there isn't all that much we can do except aggressively slow down the rate at which we're processing queries, which doesn't help anybody. And so we needed to find a way to decrease the amount of time, the amount of instances of rate limits in order to bring this back under control. So let's talk a bit about how Loki caches data. As we saw with the slide previously, when Loki ingests logs, it compresses them down into chunks and stores them in object storage. But we also, at this point, will store them in our cache. And the reason is that observability use cases tend to skew towards recent data. So if you're using logs to try and diagnose what's happening in your systems in production, generally you'll want to be looking at what's happened recently, over the last few hours, or maybe the last day or two. And so we cache all of these chunks proactively to increase the chances that those chunks will already be available to improve query performance and to reduce the number of requests on object storage. Likewise, when we query chunks from object storage in the query engine, we store them in the cache. And the reason for this is we want to try and retain as many chunks that have been recently queried as possible, because a dashboard could be active, which is requesting the same information over and over again, or we have periodic queries that run on a regular interval that are requesting the same chunks, and so we want to try and improve the likelihood of hitting these in cache instead of going out to object storage. As I mentioned earlier, observability use cases tend to skew towards recent data, and so most of the time people are looking at logs within the last 3 hours or so to find the information that they need. And we can see here that over all of the chunks fetched in this particular time range, 58.5% of them were fetched in the 0 to 3 hour bucket, 62% in the last 12 hours. And so based on this usage pattern, we decided to try and cache about 3 hours worth of data in order to serve a majority of chunks from cache. It seemed reasonable. And so we set up 200 instances of Memcached, each with 6 gigs of RAM for a total of 1.2 terabytes. And in the installation of Loki that we had, this accounts for about 3 or 4 hours worth of data. And so we thought that was going to work out pretty well. So we looked at the success metric here, which is hit rate, and we can see that the hit rate doesn't look too bad. We can see that the average hit rate per day is somewhere between 70 and 90%, and that was looking pretty good. And yet we were seeing a large amount of requests out to object storage, and so we looked closer. One of the angles that we didn't look at initially was how much is our cache churning. And by churn, I mean how many items are being evicted from the cache before we can fetch them even once. And when we looked closely into this, we found that we were churning massively. And the reason for churn is that the cache is insufficiently large to hold the number of items that we're putting into it. And Memcached is going to evict items when it becomes full. And so this indicated to us that there was a real problem and we needed to investigate further. So in this installation of Loki, we were adding about 6 terabytes of chunks per day. And on this installation, we found that it wasn't following the typical usage pattern that we saw previously in the recency bias slide. We could see here that only 22% of the chunk volume was being fetched within the last 24 hours. And if we needed to cache a critical mass worth of chunks, we would need to cache about a week's worth of data. And this would mean that if we take a week's worth of data at 6 terabytes a day, we would need a very, very large cache. We also needed to consider the network throughput going to our Memcached cluster from our queriers, and we had quite a large amount of network traffic going through. So you can see here a 7-day moving P99, and that is sitting at about the 0.5 terabit range. And so we needed quite a lot of network throughput as well. So when we were figuring out how large this cache needed to be, we estimated that we would need about 50 terabytes of cache and about 0.5 terabit of network throughput in order to serve the same amount of traffic that we had currently and retain as much of the chunks as possible before, instead of having to go out to object storage to fetch that information. And so the real challenge here was, how can we build a cache that's this large cost effectively while still maintaining performance and do it in a way that is operationally familiar to the team? If we don't satisfy all 3 of these requirements, then the solution isn't going to work out for us. So if we dive a little bit deeper into the economics of our existing solution, we'll see that our 1.2 terabytes of Memcached was costing us about $8,800 a month. Now, the scary number here regarding scalability is this number here. Each gig of RAM costs us $4.43 a month. And so this means that if we need to scale up from 1.2 terabytes to 50 terabytes, this is going to be massively expensive. So we needed to find a way to drive down the cost per gigabyte of storage in our cache. And the solution that we came up with was to use Memcached, but now use it with SSDs. Memcached has this very little known feature called Extstore, and it's been around since 2018. And in this really interesting blog post by Memcached maintainer, he talks about a lot of the economics and the performance characteristics of SSDs and how they are now an attractive proposition for use in caching systems. And the QR code here will take you to that blog post, and it's well worth a read. And the way that Extstore works is it allows the Memcached instance to spill values out to disk. So instead of trying to keep all the keys and the values in DRAM, instead what it does is it splits the keys in DRAM and the values out to SSDs. And this allows it to grow to quite massive sizes while still maintaining the same interface that it has currently. So you still use the same Memcached client, and everything works the same way from the client perspective, but from the server side, now the values are on disk and the keys are held in memory. So in order to use Extstore, it's incredibly simple. All you do is you configure a path to a file on disk, and you specify a size, and then Memcached takes care of the rest. It will divide that file up into pages, the same way that it divides memory up into pages, and then it will allocate those items there as needed. You can also configure multiple disks in order to have Extstore spread the items across many disks to try and alleviate some of the performance dynamics of SSDs, which we'll talk about a bit about later. So how do we get access to SSDs in the cloud, right? Do we use a service like EBS with a storage class that gives us SSD level speed? Well, the problem is that we can't use network attached storage like EBS. And the problem is that when we have a network involved, then there is latency, right? That's one of the big problems. There's going to be variability because now we're using a network attached storage, so that the network could have a little bit of jitter, or we could be competing with other tenants in the cloud environment for the same disks. And so we really want to try and drive down the latency as low as possible, the variability as low as possible, and get our caches as close as possible to the disk. So how do we do that? And what we ultimately want is an SSD that's physically attached to the hypervisor on which our virtual machines are running. So we run Kubernetes in the various clouds, and so the hypervisor is there to provision the pods on some physical hardware somewhere. So we want the SSDs as close as possible to those pods, and we don't want any network involved to drive down the latency and the jitter. And so luckily the clouds, the major cloud vendors all offer some version of this. And so in Google Cloud, they offer what are called local SSDs. These are 375 gigabytes in size and $38 a month. And you can attach up to 24 of these per node. So that gives you 9 terabytes-ish per node. And the performance characteristics are pretty good. And there is something similar in AWS called instant storage. Now these aren't an arbitrary number of disks that you can attach to some instance. This is now an SSD that comes with the instance type. So we use IM4GN or I4I nodes, and those come with SSDs built in, and they range in size and cost, but it works out to be roughly the same as Google Cloud. And the thing I really want to try and highlight here is that by using this solution, combining SSDs with Memcached, it was already a very familiar solution to us. We've been running Memcached for years, and we know how to provision hardware in the cloud. And so from the time we discovered Extstore to having this running in production took us just 2 weeks. And that's a really great timeline for getting a solution out like this. And it speaks volumes to how easy it was to use the SSDs provided by the cloud providers and Extstore as well. So this is what our new configuration looks like. We've got 33 instances with 5 gigs of RAM each and 4 SSDs. This is in Google Cloud. And so 4 SSDs at 375 gigs each is about 1.5 terabytes. So 33 of those together makes 50 terabytes of storage, and we get around our half a terabit of required network throughput as well. And amazingly, this comes out to be about the same price as a caching architecture that's 42 times smaller. And the reason for that is that we have this very, very low cost per gigabyte per month. And so this was incredibly exciting to us, and it ended up working out quite nicely. And as you can see that this cost us $8,700 a month, whereas the previous architecture cost us slightly more. Now, this $100 a month doesn't account for all of the cost savings that we realized as well. Object storage also contributes quite a lot to our costs because we store billions of items in object storage and we have to retrieve them. And we pay $5 per million writes and 40 US cents per million reads. And so by reducing the number of requests to object storage 65%, that's how we realized our overall TCO reduction of 2%. And as you can see over here, the number of requests to object storage massively decreased following the rollout. So let's talk a little bit more about the results. We rolled out on the 4th of May of this year, and as you can see in the couple of weeks preceding, we've got a green line and a yellow line. So the green line is the number of terabytes per day that we're retrieving from our cache, and the yellow line is how many terabytes per day we're retrieving from object storage. And as you can see, these lines pretty much follow each other, and that's because we were evicting items so fast out of our cache that we would have to go and fetch them from the store all the time. But then following the rollout, you can see a massive separation between those lines. We still had to fetch items from the store, but now we're able to retain so many more of them in our caches that we ended up fetching hundreds of terabytes of data from our caches every day. Visualized a different way, if we look at the yellow line here is now the unfetched evictions, and we can see that the churn in our caches massively decreased as well, because now we have a cache that's large enough to hold the set of data that we need. Query performance wasn't really affected all that much, which is good, but also we would have expected some uplift in performance because now we're able to access our data quicker. But this is an indication that the data access part of our database is not where our bottleneck sits right now, and so we were frankly just happy that our query performance wasn't affected at all. In fact, we saw a slight increase. Looking at the median and the P99, we didn't see too much change, so that was already satisfactory. So, as you might expect, the solution doesn't come without its trade-offs. And as you probably could have predicted, adding SSDs into our caches caused the latency to go up. Now, running in a purely DRAM-based Memcached cluster before, we were seeing single-digit millisecond P50 latency, and now, following the rollout, we start to see P50 latency all the way up to 30, 40, 50 milliseconds at a time. And so this looks really bad, but we have to consider it in the context of the request to object storage. And as you can see, the P50 object storage latency is routinely an order of magnitude higher than even the new latency from Memcached. At times they're about the same, but generally speaking, object storage latency is a lot higher at a baseline. And when you consider that you can only fetch single items at a time from object storage, whereas we can fetch batches from our cache, this latency increase is entirely tolerable to us. And just to drive home why we're seeing this increase in latency, let's look at the latency difference between main memory and SSD random reads. And we can see that accessing a megabyte of data from main memory takes about 1 microsecond, whereas fetching it from an SSD in a random read fashion, which we're doing, takes about 150 microseconds. And so, of course, there would be a latency increase by adding SSDs into the mix. But as we can see, this is tolerable to us. One other trade-off to consider is durability versus volatility. So when we're using a network-attached storage system like EBS or GCS, those are typically durable, and they're durable to 11 nines of durability or something. But with local SSDs, the durability is very different, and so I would encourage you to go and read up on the trade-offs that you have to make here. But because we're using these SSDs for a cache use case, the fact that these disks aren't durable under all conditions is completely fine for us. It's not our system of record, so if we lose one disk which contains some small percentage of our cache, that's completely fine. We're happy to throw it away. And of course, disks have their own brand of problems. Of course, disks can fill up, although Extstore can take care of that for you by you specify that maximum size that it can grow to. Of course, the disks can age out, and then sectors start to fail, and performance starts to degrade. And in situations like this, what we do is we just kill the disk, or we drain the node on which those disks are provisioned, and then we get assigned a new node with some new disks, and then we just start refilling the cache that way. And so that's the beauty of using SSDs for this use case. We don't really have the durability concern, and we aren't experiencing data loss if we throw these disks away. So again, this was tolerable to us, but it's something to note. Now, so with observability, we couldn't have analyzed this problem and put in place the solution if it weren't for the amazing tools that we build and run here at Grafana Labs. So we used Prometheus extensively here with the Memcached and node exporters. We used Alert Manager to cover our architecture with alerts so that we are alerted when things aren't performing well and when we need to take action. And then of course we used Grafana and Loki for analyzing the performance and troubleshooting and finding the solution. And we built nice fancy dashboards like this, and we can talk more about it in the Q&A if you would like. And so to finish off here, I want to talk a little bit about what are the implications for the future of cloud databases. We see that the cost is starting to become quite compelling now for using SSDs at really, really large scales. And because their speed is approaching DRAM speed as well, this is really starting to force at least us to start reevaluating some of the broadly held assumptions about when you can spill to disk and what the performance implications are, etc. We're approaching a time now when SSDs are widely available in the cloud. They're managed for you. You don't have to set up all of this infrastructure yourself. It's cheap. It's performant. CPUs are coming out now with special chips for a high network throughput, in software-defined networks. So I think the future is very bright for cloud databases, and I wouldn't be surprised if we start to see some architectural shifts going forward. So thank you very much for your time and attention, and I'll now take your questions.